Okay, so welcome to this next video in which we are discussing the function of synaptotagmin, where we're specifically looking at its interaction with phosphatidylserine. So at the end of the previous video I said that we now need to make sure that this actually happens in a physiologically relevant time course, okay? So it needs to happen very, very quickly. So what was done was another experiment by Ed Chapman. Okay, and this experiment is going to show how quickly you can get the synaptotagmin to bind to the phospholipids for the phosphatidylserine residues in the phospholipid bilayer. Okay, so this assay is going to rely on us understanding something about the amino acid tryptophan. So I'm going to just go over a brief discussion of the amino acid tryptophan, and then we'll go on to what Ed Chapman actually did. So let's start off with the structure of the amino acid tryptophan. Okay, so here is the generic amino acid structure, so the amino group, the carboxylic acid group down here, the alpha carbon in the center with a hydrogen off it. Okay, the R group of tryptophan is you then have a methylene group, like so, and then you have a structure known as an indole ring coming off of tryptophan. So, let me show this. An indole ring is basically made up of two rings that have been joined together, and the starting one is that you have the pyrrole ring. So I'll show you the pyrrole ring, and then I'll show you how it's modified to make an indole ring. So the pyrrole ring is basically a 5-membered ring, so a pentagon, where 4 of the members are carbon and 1 of the members is nitrogen. So you then have hydrogens off here, like so. So this is the structure of the pyrrole ring. So the pure pyrrole ring, if I draw it down here, is nitrogen. I'll draw its skeletal structure to save time. So it's nitrogen bound in a 5-membered ring with 4 carbons, and you have double bonds there and there. So this is the structure of the pyrrole ring. Okay, now in order to modify that into an indole ring, what you do is you bind another ring off here, okay, which is a benzene ring. So it has these alternating single and double bonds. Okay, so a double bond there, and then you have hydrogens off all of those carbons in the benzene ring. So now this structure, this whole structure here, is known as the indole ring. So let me show this. So 6-membered ring here, which is benzene, bound to the indole ring. So this is benzene at the moment, and then it's bound to the indole ring, which I'll show here. Okay, and there's that nitrogen. Oh, and we'll need to, I should have shown on the pyrrole ring actually the hydrogen off the nitrogen. You only get away in skeletal formulae with not showing the hydrogens off carbons, not off nitrogens. So this now is the structure of the indole ring. Okay, so this is then the structure of tryptophan. Tryptophan. Now, tryptophan is interesting to biochemists because it has its own fluorescence properties. So this amino acid will fluoresce, basically. Now, what is fluorescence? Fluorescence means that you can shine radiation onto this molecule of a certain frequency, known as the excitation frequency. The molecule will absorb that radiation, and then it will gain a bit of energy from it, and then it will re-emit energy. It will re-emit another photon at a lower frequency, known as the emission frequency here. That's the phenomenon of fluorescence. Fluorescence. So tryptophan is a fluorescent molecule. However, its fluorescent properties are determined by what sort of an environment it's in, basically. If it's in a lipid, a hydrophobic environment, then it fluoresces extremely well. So if you put it in a phospholipid bilayer, for instance, it will fluoresce really well. So what are we going to do? Well, basically, we're going to take synaptotagmin molecules, and specifically in this assay what they used was cytoplasmic synaptotagmin. So let me explain what that means. So if this is the synaptic vesicle here, then implanted in the membrane of the synaptic vesicle, you can have this is the alpha helix, the membrane spanning alpha helix of synaptotagmin. You then have these two domains here, the C2a domain here and the C2b domain here. This portion, consisting of the C2a and the C2b domains, this is what is meant by the cytoplasmic portion of synaptotagmin. So this is the cytoplasmic portion of synaptotagmin. So basically, what they do is they took this cytoplasmic portion of synaptotagmin. So let's say we have it here. Okay, so it has the C2a domain, the C2a domain, and the C2b domain. So I'll colour it in pink. And basically, what they did is they mixed it with liposomes, okay, which contain phosphatidylserine. So here is this liposome with phosphatidylserine, which I'll just draw as an orange blob again. So this orange blob in the phospholipid in the liposome over here represents phosphatidylserine, which remember is the molecule that the C2a domain is going to bind to when calcium binds to that C2a domain. So this is phosphatidylserine, or PS for short. Right, so what will happen is if we add calcium in here, it will bind to the C2a domain. The C2a domain will bind to this phosphatidylserine, so let's show that happening here. Okay, and it will basically implant into the phospholipid bilayer, because remember, even though I've drawn this as a great big orange blob, it's a tiny little molecule in the phospholipid bilayer. So basically what's happening is when C2a binds to this phosphatidylserine, it's actually pushing into the membrane. So the idea is that we could use the biochemical properties, the fluorescent properties of tryptophan to measure this. The idea is if we could mutate this cytoplasmic portion of synaptotagmin slightly so that its properties of binding to phosphatidylserine aren't affected, but we add on a tryptophan residue, okay? And the single letter amino acid code for tryptophan is W, so I'm going to denote tryptophan as W. That's the conventional single letter amino acid code for tryptophan. So we mutate it slightly to put this tryptophan sticking out. Now, if we then add calcium, what will happen is it will come in, 3 calciums will bind to the C2a domain, 2 calciums will bind to C2b, okay? Those will increase the electrical potential of the C2a and the C2b domains. C2a will then bind to the phosphatidylserine molecules in this liposome here, so this, remember, is the liposome. And the C2a domain will end up pushed right into this phospholipid bilayer, which means the tryptophan will end up pushed right into the phospholipid bilayer, which means the tryptophan's fluorescent properties will go up. So if we shine now the excitation frequency on this setup, then we will get more fluorescence. Basically, we'll get more of this emission frequency coming back at us, basically. So we can use that change in fluorescence of tryptophan to indicate that the C2a domain has bound to the phosphatidylserine molecules in the phospholipid bilayer of the liposome, basically. And that's what they did. And they were then able to basically add calcium in and see how quickly the C2a domain actually binds to the phosphatidylserine. And the answer they got was that it was too fast to measure. Okay, so the machinery they were using to measure this had a maximum resolution of 500 microseconds, I believe. Okay, so it could tell events apart if the time between them was greater than or equal to 500 microseconds. But if two events occur within 500 microseconds, then it can't tell them apart as having occurred at different times. So that tells us that this must happen in a time less than 500 microseconds, which is good because neurotransmission, the release of neurotransmitter in response to calcium going up needs to happen in a time course similar to that.